This is a theorem, but in a atypical sense of the term. It's actually the central result in the field of hardware support for virtualization. In other words, the ideal requirements that you have on a computer hardware in order to support efficiently virtual machines. So what do we mean by virtual machine? Let's first actually define what we mean from a hardware support by an operating system. So this is a very basic diagram of the way we think about how an operating system runs on a computer. You have the computer hardware, the CPU, the memory, the I/O subsystem, and then there's a piece of software that actually directly controls the hardware resources, and that piece of software is the operating system. And the main function of the operating system is to run applications, and you can run multiple applications on the same operating system. Now, what do we mean by virtualization? Well, virtualization is about the ability to run virtual machines. And a virtual machine, first and foremost, is an abstraction. So I'm going to draw the abstraction of a virtual machine as this black box. This abstraction is sufficiently equivalent to the underlying hardware that you can actually put an operating system within the abstraction. And obviously, an operating system that runs applications. So since this is just an abstraction or a concept, let's actually draw a second one. So here what I've just drawn is two virtual machines running on one computer. Now, how do you actually do that? Well, you need a piece of software that actually materializes the abstraction of the virtual machine, and that piece of software is conventionally called a virtual machine monitor, sometimes a hypervisor. And the way virtual machine monitors have been defined is that they need to meet three fundamental requirements. The first requirement is that of equivalence. And by equivalence, we mean that the virtual hardware that is created by the abstraction needs to be sufficiently equivalent to the underlying hardware that you can actually run the same software in the virtual machine that you would normally run on the regular computer, and specifically the same operating systems and the same application. The second key requirement of a virtual machine monitor is safety. And by safety, we mean that the virtual machine must be completely isolated from other virtual machines and completely isolated from the virtual machine monitor, so that you can actually think of the virtual machine as if it was running truly on a distinct piece of hardware. And the third requirement is performance. And by performance, we mean that the overhead associated with virtualization, the introduction of that level of indirection, must be sufficiently small that you can use a virtual machine in the same way that you would actually use a regular computer. In other words, the slowdown associated with virtualization must be sufficiently small that it doesn't impact execution in practice. So the central question of the Popek-Goldberg principle is whether you can actually build a virtual machine monitor for a given computer architecture. In other words, is it possible to build this VMM for a given piece of hardware? And the motivation for this paper, for this 1974 paper, was at the time virtual machines were very popular, and on some computer architectures you could actually easily write such a VMM, and on other architectures, for a combination of reasons, it was actually either difficult, impossible to write a VMM, or the VMM that you could actually end up with had some compromises. For example, it violated somewhat the equivalence property, or it had issues or complications associated with performance. So to explain the theorem, we first need to define slightly more precisely what we mean by the hardware, and in particular the processor requirements. Let's actually first work through the processor requirements and the minimal set of requirements that you have in order to run a protected operating system. And so in blue you have the operating system, and again in orange the applications. You clearly need to protect the operating system from the applications, and you do this by using a combination of two mechanisms. The first mechanism is that there is a bit in the CPU somewhere that tells the CPU whether it is running in kernel mode or whether it is running in user mode. So beyond that one bit that specifies whether the CPU is running in kernel mode or in user mode, the other fundamental prerequisite to the existence of a protected operating system is the availability of virtual memory. Now, virtual memory is about adding a level of indirection between the address space that the processor uses, which is the virtual address space, and the underlying memory that is implemented in silicon, which is the physical memory. And there are many ways in which virtual memory can be implemented. The most common way in which this is done on current computers is through a mechanism called paging, which is implemented by the memory management unit, or MMU, of the CPU. There's actually a simpler mechanism which is called segmentation, which can also implement virtual memory. And segmentation is simpler because it relies only on two privileged registers to define the virtual address space. And these two registers are the relocation register and the bound register. And with those two registers, you can allocate a piece of physical memory that is mapped in your virtual address space at virtual address 0. The relocation register specifies the offset, and the bound specifies the extent of the virtual address space. Now, you actually need a few more things in order to to run an operating system on a computer beyond that one bit that specifies whether you're in kernel mode or user mode and virtual memory. You need a way to go between user mode and kernel mode, and a way to go between kernel mode and user mode. And this is conventionally known as the trap architecture. So you need to be able to take traps, which is transition from user mode to kernel mode, and you need to be able to return from exceptions, or from traps, which is the inverse operation. And in those transition, the kernel user bit is updated, and in those transition, the operating system must also have a mechanism to change the relocation bound registers, so that you change the address space of the application as you resume execution of the application. So to summarize the minimal requirements to run an operating system, you need three things. The first one is this bit that specifies whether you're in kernel mode or in user mode. The second one is you need virtual memory, for example, using the relocation bound register pair. And the third is that you need a trap architecture that allows you to transition between the two. And so the key question is, what are the additional requirements necessary to run a virtual machine monitor? So here I drew, again, the conventional architecture where you have the virtual machine monitor, two virtual machines, each with their own operating system and their own applications. Virtual machine monitors are constructed using a technique known as direct execution. And by direct execution, we mean that the virtual machine monitor does not interpret the execution of the instructions of the virtual machine, but instead the virtual machine monitor runs the virtual machine directly on the hardware, and the instructions of the virtual machine, whether it is the operating system or the applications, execute directly on the hardware. If you think about direct execution is the way operating system allow application to run at full speed in user space by letting them run directly on the processor architecture. We're extending the concept of direct execution to run the entire virtual machine directly on the CPU. Now, that gives you performance. You obviously need to have safety as well. And therefore, what you need in order to guarantee safety is you need a level of protection between the virtual machine and the virtual machine monitor. Now, you also need equivalence, and so you need to provide an abstraction that is equivalent to that of the underlying hardware. The underlying hardware assumes that there's protection between the operating system and the application, and so there's another level of protection that is required between these two entities. And so the key question is, do you need more than this single bit that separates between kernel mode and user mode? And the answer is actually not fundamentally. And let me explain why. Well, you can obviously run the virtual machine monitor in kernel mode, and that is how virtual machine monitors normally run, or always run. But then the virtual machine monitor can actually run the operating system, which is designed to run in kernel mode, in user mode. It can also run the application, which is expected to run in user mode, in user mode. Now, when we actually change the operating model in this particular way, there are a few fundamental implications. One is you still need to keep protection between the application and the operating system. So these two user modes need to be somewhat distinct, and specifically, the virtual address space that is running must be handled separately. And the second observation is that the operating system is always designed to run in kernel mode, and by running in user mode, the behavior will change. So for example, some instructions that are intended to run in kernel mode don't run normally in user mode, and so if the operating system attempts to execute these instructions, those will generate a trap. And the trap will be handled by the virtual machine monitor. So a virtual machine monitor that runs the virtual machine directly, that relies on direct execution, is also known as a trap and emulate architecture. And by that I mean that the virtual machine monitor handles traps that are the result of the operating system executed in a deprivileged mode of operation. And the virtual machine monitor must then emulate, but only those very specific instructions that actually have led the trap. And those instructions are known as privileged instructions. So when that leads us to the classification of instructions. So up until now, I have not formally defined how kernel mode is different from user mode. And the short answer is that instructions are categorized into two groups. You have privileged instructions, and these instructions always trap if you run them in kernel mode. And then you have non-privileged instructions, and these instructions can execute either in kernel mode or in user mode. And so by changing the level of privilege by which the operating system runs, privileged instructions of the operating system generate traps. Now, this still doesn't tell us whether we can build such a VMM. And to actually solve the theorem and to formalize the theorem, we need to classify instructions in a orthogonal way, and in three particular categories. So an instruction is control sensitive if it has the ability to access, either read or write, the control state of the architecture. Now in our case, in this very simple computer model, the control state of the architecture is the bit that says whether you're in kernel mode or in user mode, and then the relocation and bound registers which define virtual memory. If an instruction can access these bits, it can know whether it is running in a particular environment, and if you are running in a virtual machine rather than on the underlying hardware, these settings will fundamentally be different. And so control sensitive instructions form an important class of the architecture. The second class of instructions are known as behavior sensitive. So a behavior sensitive instruction is one whose semantic varies depending on the settings of the control registers without directly accessing them. So a classic example would be an instruction that returns the physical address of the given virtual address. If you think about this, this is simply a number. On a 32-bit architecture, it would be a 32-bit number. On a 64-bit architecture, it would be a 64-bit number. But that number actually leaks some information, and the behavior of that instruction will be different based on the value of the registers that define virtual memory, and specifically based on the value of the relocation register. And if such an instruction exists, it is called a behavior sensitive instruction. And then instructions that are neither control sensitive nor behavior sensitives are regular instruction, and this is the remaining of the class. And this brings us to the theorem itself. And the theorem is very, very simple. If the union of control sensitive and behavior sensitive instructions is the subset of privileged instructions, then you can build a VMM. So let's think about this for a while. Well, first let's take the case where you have a control sensitive instruction that is not privileged. For example, one that reads the bit that says whether you're in kernel mode or in user mode. Well, clearly if such an instruction exists, and if that instruction is executed as part of the operating system, the answer will be different whether you're running in a virtual machine or not in a virtual machine, and therefore you violate the equivalence property. Let's take the example of a behavior sensitive instruction that is not privileged. For example, one that returns the physical address for a given virtual address. Well, if the relocation register is different in hardware than the one that is specified by the operating system, then the answer will be different. And in that case as well, the equivalence property has been violated. And so we can find counterexamples that show when building a virtual machine monitor using exclusively direct execution actually cannot be done because of the violation of the equivalence property. But in order to prove the theorem, we also need to convince ourselves that if the inclusion relationship is met, then you can actually build a VMM. And so for that, we actually need to construct the VMM, and the proof, and the formal proof in the paper, is actually a proof by construction, by formally demonstrating that you can actually build such a VMM, and that such a as long as the inclusion relationship is held, then such a VMM can be built. Now, I've already illustrated elements of that VMM, in particular the fact that it is the entity that is running in kernel mode, that it is running the virtual machine always directly in user mode. The VMM being in kernel mode handles the traps. All transitions between user mode and kernel mode are handled by the VMM. Instructions, for example, that are intended to have a transition between the application and the operating system, let's say a system call instruction, normally is a transition between the application and the OS. In this case, the way we implement a system call instruction is this is a trap. All traps are handled by the VMM. The VMM emulates the semantic of that instruction, so it decodes the instruction, recognizes that this is a system call instruction, and changes transfer of control into the trap handler of the operating system itself. And therefore, you can make forward progress by emulating the system call instruction. So transitions are one thing, but the virtual machine monitor also needs to virtualize memory appropriately to run the virtual machines. And what the virtual machine monitor specifically needs to do is to virtualize physical memory. So we're adding a level of indirection within the memory hierarchy. So in a non-virtualized architecture, as I mentioned, you have a level of indirection between virtual memory and physical memory. Well, when you introduce virtualization, you add yet another level of indirection, and that is between the physical memory that is managed by the virtual machine and the actual physical memory of the computer. And to disambiguate these two concepts of physical memory, people have introduced a qualifier, and that is why people refer now to guest physical memory and host physical memory. Now, in a segmented architecture with a relocation and bound register pair, the operating system controls and specifies the VM's relocation register and bound register, but the VMM actually controls the hardware relocation and bound register. And the VMM actually sets the values of the relocation and bound registers in hardware as follows. So the virtual machine is designed to run more than a single virtual machine at a time. And in a segmented architecture, the way you would do this is you would allocate the physical memory, and by that I mean the host physical memory, into different chunks, and each chunk is associated with a particular virtual machine. So there is an offset in host physical memory that corresponds to the beginning of the guest physical memory of each virtual machine. There's also a size of the guest physical memory that is specified by the VMM when you start the virtual machine. And so the virtual machine itself has two parameters that are not visible to the virtual machine, not defined in the architecture, but maintained by the VMM. And those are the address in host physical memory of guest physical location 0 of each virtual machine, and the size in guest physical memory of each virtual machine. And with that, you can actually easily work out the invariant that is implemented and enforced by the VMM when the virtual machine is running. And that invariant is that the relocation register itself is the offset in physical address space of the virtual machine plus the virtual machine's own relocation register. So as for the second register that defines virtual memory when you're running the virtual machine, the bound register, well, fundamentally it is specified by the virtual machine itself. So it is the virtual machine's own bound register. There's actually a corner case, which is you cannot allow the virtual machine to access more than the amount of guessed physical memory that has been allocated to it. So in reality, the bound register is the smallest value of the one specified by the virtual machine and the amount of space that is available within that particular virtual machine. Now there are details of this in the paper, but I've covered the fundamental aspects that are actually required to build this VMM. You need to handle traps, execute the virtual machine directly, and enforce the invariant so that memory, in particular guessed physical memory, can be virtualized while maintaining the safety property. So this theorem is actually not very complicated, and in many ways it is very intuitive. If you have a mechanism in which you can leak whether you're running in kernel mode or not, or leak any information as to whether you're being virtualized, then it's impossible to guarantee that you can meet the equivalence property that is necessary to build a virtual machine monitor. And nevertheless, this paper is considered the central contribution in the field of architectural support for virtualization. And there's a reason for this, or there's a context for this. The motivation for this paper was that, as I mentioned at the very beginning of this presentation, is that architectures were being developed in the 1970s, and some of them could support VMMs and others could not. And the example that was used by the authors in 1974 was the PDP-10. Now, the PDP-10 is a long retired computer that only belongs in a museum today. Since the paper has been published, many popular architectures have been introduced that also violated this principle. So the popular RISC architectures, for example MIPS, have also violated this principle. In the mobile space, the ARM architecture was introduced and violated the virtualization principle. And in the desktop and server space, obviously the x86 architecture was also introduced and violated these principles. So even though the paper was published in 1974, the most popular architectures that have been introduced since then have still managed to violate the architectural principles and the minimal requirements necessary to run a VMM, and specifically a VMM that relies only on direct execution and maintains safety and equivalence. Now, the reason for that was that virtualization and virtual machines were not important for a few decades in the history of computing. Things have changed starting back in the late 1990s with a return of interest in virtual machines, and which is why these architectures have now evolved, and they now provide architectural support for virtualization. For example, the x86 architecture has added virtualization extension known as VTX, extended page tables, and a virtualization of the I/O subsystem known as VTD that provide end-to-end architectural support for virtualization. So if you're interested in going into the details of the theorem as it was published in 1974, I recommend that you read the paper itself. This was published in Communications of the ACM.